Good morning. This lecture will cover Chapter 18, Section 8. This is the material that we'd be covering Wednesday, March 25th in class. So that's in Chapter 18, Section 8. And the topic for today's discussion is complex ions and complex ion equilibrium. So this is the last type of equilibrium that we're going to be looking at, and it deals with the formation of these things called complex ions. Now, we've had some experience with complex ions in lab. For example, you saw the formation of iron thiocyanate here in one of our equilibrium labs. And we've seen other sort of things like hydride complexes when we talked about high charge metal ions affecting the pH, etc. So we've seen these kind of complexes before. And we're going to be looking at the equilibrium between these of these complexes. And so a little bit of background first. So transition metals, right, tend to be what are called good electrophiles. Now, the term electrophile means that it is attractive to electrons, right? It wants electrons. And so transition metals being positive, these transition metal centers, right, they want to attract electrons. And so as a result, they will often bond to one or more water molecules if they're in an aqueous solution to form a hydrated ion, right? So when we have these metal centers, these metal cations, typically in solution, they aren't just there by themselves, right? They are typically coordinated with multiple water molecules. Now, we can display this equilibrium as shown here. So the water molecule acts as a nucleophile, meaning it's attracted to a nucleus or a positive charge, like the metal center, and it's donating a pair of electrons to the metal center, right, the electrophile. So we have the metal being an electrophile wanting electrons. We have the water in this case acting as a nucleophile wanting to donate electrons, right? Now, when this happens, we form what's called a coordinate covalent bond. So this is just a special kind of bond that we talk about in these transition metal complexes, right? Where the electrons are shared between the metal center and this, in this case, the water. Right? Now, the equilibrium itself is between the separate complexes, so in this case, the metal center and the water, and the complex ion on the product side. Now, notice that water is a neutral molecule, so when it coordinates to the metal center, it doesn't change the overall charge. So when this silver ion coordinates, in this case, two water molecules, it still retains that positive one charge. So many metals do this, and water is not the only material that can coordinate to the metal center, right? All kinds of materials can do this. So we see an example here of thiocyanate, the SCN ion that does it. We can also have ammonia and many others that fall into this group that we, as a class, call ligands, right? And these are ions or molecules that can act as nucleophiles and bond to these metal centers. So water is one example, and we'll see other examples as we go through some different examples. So if we look more closely at this equilibrium, certain ligands have a stronger ability to bond to a metal center than others. So for example, if we take that silver water complex and we mix it with a solution of ammonia, right? ammonia forms a stronger bond to the silver than the water does. So what we see is we see the replacement, right? We see the ammonia coming in and ultimately kicking out the water and replacing it, giving you a silver ammonia complex and free water. And so we can utilize this ability of different ligands to bond with different strengths to add ligands to a metal center, to replace other ligands on a metal center, etc. Right? And you'll see this is also an equilibrium process, right? Now, you might also see the equation written like this, where we negate the water for simplicity. So sometimes we'll just see it written as the metal center plus, in this case, say ammonia, goes to the complex ion, right? So this is kind of how we saw it when we had the iron thiocyanate ion, where we had iron 3 plus the SCN minus 1 ion in equilibrium with the FeSCN 2 plus complex ion. Now, I want to point something out here that notice that SCN is an ion, right? A -1 ion. And so when it forms a complex with the iron, right, notice the charge on the complex ion has changed, right? It has gone from the positive charge, +3 charge on the plain metal to only a +2 charge on the complex ion because of the negative charge on the ligand, right? The -1 cancels out one of the positives, so the overall charge when you combine these is a 2 positive. So if our ligand is an ion, it's going to affect the charge of the overall complex ion, and it will be different than what the metal center is. If we have a neutral ligand, like we saw with ammonia and water, then the charge on the metal center is going to be unchanged, and it will be the same in the complex ion. So we have to be careful when we do that, that we get the right charge on the complex ion based on the ligand that's bonding. So now the equilibrium itself. So the equilibrium between the free species and the complex ion is called the complex ion formation reaction, right? And the equilibrium constant for this is called a formation constant, or abbreviated as Kf. And of course, our equilibrium expression is going to be, as always, products over reactants. So it's going to be our complex always on top, and then our individual species, the metal center and our ligand on the bottom. Now, the coefficients, the powers will change based on the coefficients of our species. So in this case, there's 2 ammonias for every metal center, so we have a squared. So this power will vary depending on how many ligands can bond to that particular metal center. If we look at a table showing a bunch of these different formation constants, one big obvious thing that I want to point out is notice the values, right? A lot of the other equilibriums that we've looked at have had very small values, right, with negative exponents, right, indicating that those equilibriums are very reactant favored, such as the acid ionizations for weak acids or the solubility equilibriums that we just looked at, right? Those all were quite small numbers, right? Notice here, all of these formation constants that we're showing are very large numbers, right? Much, much bigger than 1, right? Indicating that the formation of these complexes is very favored, right? These are very product-favored equilibriums. Now, the one thing that allows us to do, right, is that this opens up the formation of these complexes as a possible way to increase the solubility, right? Now, how might that work? Well, let's look at this example. So if we look at the solubility equilibrium of silver chloride, right? So in the last section, we looked at, an ionic compound dissolving to give us our ions. So the KSP of silver chloride, is quite small, 1.77 times 10 to the minus 10, right? This is something, if we look at solubility rules, would be considered very insoluble, right? Now, however, if we look at the formation equilibrium of silver ions with ammonia, right, this is a very positive equilibrium, right? 1.7 times 10 to the 7. So this is very product favored. So while this equilibrium is reactant favored, this one is quite product favored. So by combining these two ideas, what we can do is we can force more of this complex to go into, more of this ionic compound to go into solution by taking advantage again of Le Chatelier's principle. So if we add ammonia to this, it's going to complex with this silver ion, right? So in other words, it's going to remove the silver ion from solution by forming this complex. Now, of course, how is the system going to react? As we deplete the silver ion, right, then this equilibrium here is going to not be as reactant favored, but is going to start to become more product favored as we try to form more silver ions in solution. Now, of course, this is just going to continue. If we add more ammonia, we're going to continue to pull silver out of solution, or out of the free silver out of solution, and it's going to be tied up in this complex, and that's going to pull, again, more silver ion into solution, and ultimately pull more silver chloride into solution to dissolve. Now, if you remember back to chapter 16, when we add up two reactions, right, in order to find the overall equilibrium for the sum of the two reactions, we have to multiply the two K values. So if I look at this overall process, I'm going to take my KSP, my 1.77 times 10 to the minus 10, and multiply it by my KF of 1.7 times 10 to the positive 7. And it's going to give me a new K value, or an overall K value, of 3.01 times 10 to the minus third. So now I have an overall equilibrium that is more positive, or more product favored, if you will. It's bigger than what my original KSP value is, indicating that I'm going to create this more soluble, I'm going to pull more silver chloride into solution. So by combining a formation equilibrium with a solubility equilibrium, we've increased the solubility of these compounds. So if we were to draw out sort of the overall equation here, we would end up with silver chloride solid plus 2 ammonia in equilibrium with our complex plus chloride ion And so our net effect is still dissolving the silver chloride, but by combining it with this complexation, we have a much more product-favored equilibrium with this equilibrium constant, as opposed to our only our KSP without the ammonia, which is a much smaller equilibrium constant. Now we can see this in picture form if we look at what it would look like if we just try to dissolve silver chloride, right? It's essentially insoluble, right? But if I add in some ammonia here, all of a sudden, if I add enough ammonia, I can pull all of this silver chloride into solution as this ammonia complex. And so this is a very useful technique to make ions that we couldn't get into solution. So if we want to try to get this silver ions into solution, the silver chloride won't dissolve. But if we transform it into this silver complex ion with ammonia, it's much more soluble. So we can pull the silver chloride into solution by simply adding this other ligand, taking advantage of this very product-favored complexation, complex ion formation. We just looked at one type of very common problem that we can use with these KF equilibrium, that is to combine it with a solubility equilibrium to reduce or to make it easier to dissolve those materials and to increase the solubility. Now, another type of problem is simply to look at the KF itself and see, how well the complex ion, how well the complexation works. So basically what you'll see here is we're going to be testing the idea that if we use a large enough concentration of our ligand, that we can essentially get all of the metal into solution. Now, it is an equilibrium, right? So we might suspect that there'll be a small amount of metal left, and that's what we're really going to check here. So if we look at our problem, notice that we are mixing two aqueous solutions here. So unlike some of the problems that we've had to do, this one we are actually going to have to do a dilution, right? Because similar to what we've done in lab. So we're going to have to calculate the new starting concentration based after we mix these two. We can't just use the given concentrations because we're mixing two solutions. So here's our equilibrium. We have nickel ions combining with, in this case, 6 ammonias, right, to form this metal complex here. We're going to calculate the diluted concentrations of each species. So we're going to do our dilution calculation, calculating M2 here. So we plug in this case, our original out of the bottle concentration for the nickel, the volume of the nickel solution that we're using, and our total volume, right, which is 300 milliliters, the sum of these two volumes. And we get our diluted nickel, right? So this is our starting nickel concentration once we have the solutions mixed. We do the same thing with ammonia using its initial concentration and volume. And we have the new ammonia, or the initial ammonia concentration in that 300 milliliter sample. So we're going to use these, and as we approach this, we're going to make an assumption, right? Our approximation is as follows, that all of the nickel is going to be complexed to form our complex ion. Now, so this is our assumption. Now, that assumption seems to be valid because we have such a huge concentration of ammonia compared to the nickel, right? So, 100 times more nickel or ammonia than we have nickel. So we have, we need 6 times as much, and we have many, many more times that. So we're going to make the assumption that we have so much ammonia that effectively all of this will be complexed. Now, of course, we're going to test that by calculating the trace amount of metal that might actually be left after it. So here's how we do it. We use our initial concentrations. We make the assumption that all of this nickel here turns into complex ions. So if we started out with this concentration of nickel, all of that concentration is now going to be in the nickel ion. So our initial nickel concentration becomes our final or equilibrium complex ion concentration. So we actually know the change here. So stoichiometrically, right, we can subtract that, and we know theoretically, it should equal 0, but we're going to see if it really, we're going to pretend that it doesn't exactly go to 0. And this is going to go down by 6 times. So this is effectively 6x, right? And so if we do the math, we subtract 6 times that from this, we get 0.117, or sorry, we get, 0.117. And we have 4.88 times 10 to the negative third here. So if we go through here and do our math, we get 4.88 times 10 to the negative third over x times 0.117 raised to the 6th power. Now, over here, this is our Kf, right, which we could look it up on our table. So this is the Kf for the formation of nickel ammonia complex. If we go through and solve this, we raise that to the 6th power. We solve our math. We get x equals 9.5 times 10 to the negative 6 molar. So this tells me that this is how much nickel would be left in solution at equilibrium if we use this much ammonia complex. Now, since our 0.0117 here, right, is much, much bigger than 9.5 times 10 to the minus 6, then we can presume that this approximation is correct, right? So looking at this, just to summarize again, we can conclude that our approximation was good because our amount of metal left in solution, right, is much, much smaller than our initial metal ion concentration, right, the 4.88 times 10 to the negative third. Therefore indicating that this is a very product favored equilibrium, right, because Kf is big, right, makes sense that we're going to have a very small amount of metal left in solution. So that wraps up the material for chapter 18. So again, I would encourage you to be working on the homework assignment. Right? That homework assignment is due coming up here next week. So be checking Talent for that exact due date and be working on that homework assignment to turn in. Again, if you have any questions about this material or the other material that we've talked about in chapter 18, contact me, email, remind, or check into one of my Zoom office hours, which I'll be holding on Friday and going forward next week. At least 3 days, probably Monday, Wednesday, and Friday, or maybe Tuesday, Wednesday, and Friday. I will be posting those. So just look for those if you would like to ask a question that way. Have a great day. Thanks.